Okay. Very good. So let me try and remind you a little bit of what we did last time around. So we were looking at partition functions, right? We were looking at partition functions and we were trying to impose a modular invariance. So the first example we had where we were looking at just the free boson, and we found that the partition function, the naive thing that you wrote down, would have been given by this modulus of this eta function squared, 1 over that, okay? Now we demanded that the partition function be invariant under uh, modular transformations. This is something that we saw should be generically true, and so since T and S actually generate the modular group, we will it's suffices to check that the Z is actually invariant under TNS. Speaking about TNS, since a few of you had questions, I sort of dug up some literature where a proof of this is done, and I will circulate that, okay? Okay, so moving on. So we know actually something that you're going to derive is the modular properties of eta is something that we know. And once we try and see, once we just try and see what exactly that would mean for the partition function, we see that since eta is not modular invariant, so the partition function that we defined before will not be modular invariant. In particular, if we are looking at the S transformation, then we will see that there is an tau inverse which sits in front when we do this S transformation on the Z. So in order for us to be able to define something which is modular invariant, on top of doing this, I mean 1 over eta squared, mod eta squared, we have to put in a proportionality factor, and that is 1 over imaginary tau. Now you can check that under modular transformation, this indeed will be modular invariant. And you can actually do this more cleanly if you wish. I mean, it takes some amount of more work, but I refer you to the book by Di Francesco et al. Good, this has my, okay, no, the book by Di Francesco et al. For details of this, all right? So the upshot is that this free boson partition function looks like this. Now then we went on to trying to understand things like, see what is going to happen if you put the free boson on a circle. Then what we saw that when we do an identification like this, it leads to the fact that there are going to be non-trivial, I mean, changes in the weights under J0 and J0 bar. So this is going to give you delta, but this is going to give you something that reminds us that this guy actually winds around this compact direction. So when you take that into account, the circle partition function is going to be 1 over eta squared again, but it'll have these extra pieces. Now again, what we do is we demand a modular invariance, and then what we see is that if we look at the invariance under the T transformations, the circle partition function actually picks up a phase. Now we need this phase to vanish in order for this to be, invariant. So that restricts what these deltas can be, and then that means that the spectrum is actually is actually sort of constrained by looking at this this particular T transformation. And J naught and J naught bar are now given by these guys. Now you see which is, so there'll be some effects of this non-trivial sort of winding. You can think of these things if you're looking at string theory. These are sort of states which are called, which corresponds to strings which are winding around this particular compact direction. So that's that. And you can now plug those in. And what happens is that this is something we didn't show, but you can show that it's actually invariant under S transformations as well. I told you that there is a particular interesting property out here, which is called duality, which shows that if you have a circle of size r and if you have a circle of size 2 over r, the partition function stays the same. So that's something again which can be reinterpreted in terms of string theory, and the fact that the string would not be able to see would have an equivalent description for a circle of R and a circle of size 2 over R. So in a sense, if you take R equal to root 2, that's sort of like the minimal length that the string can actually resolve. Very good. So we did this, and at the end, I didn't quite get to this, but I wanted to say a little bit more about free bosons when R is equal to root 2k. In that case, we're going to start off with chiral states, which are annihilated by L naught. That just means that you are going to have a spectrum of states that satisfies M is equal to Kn. If you do that, the partition function actually is going to simplify, and it's going to give you it's going to be written in terms of this. If you wish, these theta functions, and it's going to be given by this mod of theta k squared. So if you have k equal to 1, in that case, this particular k equal to 1 partition function is a sum of these two terms, which is theta 0 1 by eta squared and theta 1 1 by eta squared. And this is particularly illuminating when you know what are called these characters. So what is this object? This character of an irreducible representation Hi with highest weight Hi is actually defined as very similar to the partition function, but notice that here now the trace is only over the Hilbert space, which is built out of HIs and not the other things. So the natural thing is going to be that the whole partition function will be a sum of these guys. Okay. So for example, we can straightforwardly see that k equal to 1, the thing that I wrote down for you here, is going to be the sum of these particular two, chi 1 naught and chi 1 1, where these guys are given by these theta functions by the eta functions. So that's sort of like the characters of so the Virasoro algebra, the characters of them are defined in this way. So you can write down the partition function in terms of these objects, these guys. And the fun thing is now, if you know, for example, what exactly these guys, what the modular properties of these characters are, then it in turn allows you to infer what the modular, how you're going to restrict things such that Z becomes sort of modular invariant. So it gives you a way of trying to put together left movers and right movers, if you wish. So let me quickly go through a few things here. I mean, it's not going to be very illuminating until unless you sit down and do this by yourself. But let me just say that when you are looking at these uh, theta functions, uh, you know, mathematicians have actually found what the modular properties of these particular functions are. And then, so what you get is that these guys, so under T transformations, they can pick up some phase. Under an S transformation, something more interesting happens, and you have something which where these guys go into a sum of the rest of these theta functions. These are weighted by something called the modular S matrix, and this is what you get. Okay, so again, I'm not going into how you prove this, but this is something that you get. So the S transformation is essentially of a form like this, where this S M M prime is this I mean particular matrix, right? So now if you just go back to the modular modular transformations of these guys that we wrote down out here. Again, so this is something that you know what the modular properties of this are, you know what the um, modular properties of the eta are. So you can write down what the modular properties of the chi would be, and you see that there is going to be such that this chi will be given by this modular S matrix into the sum of. So this is going to be rotations, if you wish, in field space, and I mean in this particular space, and this SMM in this case will be given by this particular matrix. Again, you can check this. You can plug things back in here. So this is something that you know, and you'll also know how these eta functions, I mean, also transform. So that uh, leaves you, I mean, in a sense, this square root of I tau that just drops off, and you're going to be left with just this particular SMM matrix. So you can write down the k equal to one stuff as this these particular chi naught chi one into some matrix. In this case, that's just straightforward, and that's just a diagonal matrix, and into the bars of this. So in a sense, this is I mean transpose of the vector, and this is bar of the vector. And so what is happening is that you see that if you do the S modular transformation of this guy, what you get is that this goes into something like this. Okay, and if you are to now look at how these two are now going to be related, if you want to equate this and this, that means S transpose M S star should be equal to M. Also remember, S is a symmetric matrix. So what you have actually is S M S S dagger is equal to M. And so this sort of a thing actually gives you very, stringent ways how the left movers and right movers, will actually be sort of brought together. In the example that we give, this M is just one, so it's sort of trivial out here. But for a more sort of a generic case where you're looking at a generic case, this actually gives you a way to put together things such that this particular identity will have to go through. Okay, so you see that if this particular thing in this case was just one and you didn't have much to do, but for instance, if it were not one, if it were some other matrix that you would have got, then you would have had to do more work. Okay, So you'd see that, so what is happening is that, I mean, modular invariance will impose strong conditions on how you fix up, I mean, how you're going to look at things, such that the left sector and the right sector of a CFT partition function can be glued together. And this is useful. This is a useful thing. And it's a little formal, but I think, going forward, you might find this useful. Okay. So this is a little bit that I wanted to do to sort of, this was supposed to be where I finished out the last class. So that's what I just wanted to say for the free boson at this case. And this sort of like, I mean, a little more, I mean, advanced stuff, but this is sort of like what is called the modular S matrix. There are things like the Verlinde formula and so on, which relate the, I mean, this particular modular S matrix with fusion rules that we've seen earlier. Unfortunately, we don't have time to go into all of that. So the upshot of all of this, in a sense, is that we have seen that, I mean, modular invariance plays a crucial role when we try to understand what the partition function of a CFT is, right? Now, to end this particular discussion, I will be focusing on something which is actually very important, and it is something that is going to play, I mean, has played a very crucial role in trying to understand things that we're going to be doing at the end of this course in the last two lectures. That is, I mean, how theories of, the theories of gravity in one, I mean, higher dimension may actually be related to all of this, okay? So what is the thing that we want to do? We want to figure out, so what we are going to be doing next up is called something which is going to be related with the counting of states, and it's going to be called the Cardi's formula, okay? The idea is what? The idea, so let me first clarify this and then go on to the details. So it's not much of a leap now. So what is going to happen is we are going to, so what if you write down the modular invariance, in terms of, say, what the what the temperature of the theory is. This is something that exchanges beta with 1 over beta, okay? So this is something that you can see more clearly if you write, tau as theta plus I beta, or if you wish, if you write tau as I mean just I beta, you would be able to see how this. So then what happens is, if tau goes to minus 1 over tau, so this essentially means beta goes to 1 over beta. Okay, so the S, I mean S. So now beta is what? Beta is 1 over t, right? So this essentially means that there's a t going to 1 over t like symmetry, which is there when you're going to define things on, on this, T2. So if you're looking at theories on the torus, there's this weird symmetry that arises, and between the fact that when you are looking at low energy states with extremely high energy states. So at extremely, high energy, so the partition function is going to actually sample all states. So what happens is that because of this particular, modular invariance that you have, just information of states which are low lying can give you the information of the whole, the whole spectrum. So you can get a handle on what the number of states that are there in two-dimensional CFT is by just looking at the partition function and imposing modular invariance. Okay, so this is a very important thing. So just by looking at symmetries, just by looking at modular invariance in this case, these S transformations, we would be able to write down for you what the entropy of the system is, in the sense that you would be able to write down how many states there would be of a system. Remember that we have not written down an explicit Lagrangian, we have not written down an explicit Hamiltonian, we have not really done anything at all except for imposing symmetries. And just by doing that, without even referring to any particular system, for any two-dimensional CFT, we would be able to write down what the entropy of that system is going to be. So this is, I mean, this is the little trick that I'm going to describe in these next few minutes. But I just wanted to pause to just give you the significance of this. We have not done anything. We're not specifying the system at all. We are specifying symmetries. And from that, we can get an idea of what, I mean, you know, what the entropy of the system is going to be, okay? So if you wish, if there are any questions, I'm happy to try to answer them. I mean, otherwise I'll just go ahead and try and prove this stuff. Okay. Let me for the moment then try to give you an idea of how you can come to this particular formula. So now we have seen that Z naught, which is this particular quantity, this is going to be invariant under modular transformations. Okay. Now we're going to define the partition function of a torus with modulus tau slightly differently. We're going to strip off these central terms. Okay. So if you wish, we are defining Z as a trace of e to the power 2 pi I L naught minus 2 pi I tau bar L naught bar. This is given by rho h bar e to the 2 pi I h tau e to the 2 pi I tau bar h bar. Now this is essentially, so what this is that you want to look at this on some states h bar, and you want to do this. Okay, so this is essentially means that as you have seen, so let me not write the whole thing. So this just means you're doing with you know, h i's, if you wish, and e to the 2 pi I tau L naught h I, and you sum over all i's. Okay, so this is what this is. And so once you do that, once you take this L naught, so what you have at the end of the day is 2 pi I tau and h. But also you will have something which is rho of h, which sort of would multiply this, because rho of h is the number of states that are there with an eigenvalue h bar. Okay, so this is the sum that we are trying to do. Very good. So this is what it is. Now, what we are going to be doing is we will extract rho from Z by looking at by integrating. So we are going to do I mean contour integral. We're going to treat tau and tau bar as independent I mean complex variables, and you know do the usual thing of q equal to e to the power 2 pi I tau. So this is simple, right? So if you have something like this, you can just invert this to bring rho h bar into an integral of this form. So this, as you can clearly see, is you're just going to pick up the residues at the poles. So it'll just, you know, you can just plug this in out here, and then you sort of get rho equal to rho if you wish. So that's what it is. And what we're going to do is we're going to drop this tau bar dependence, and we can restore it at the end. Okay. Now is you know we're going to play these tricks now. Okay. So the basic trick is to notice that tau of z I mean z of tau, not tau of z, which is exponential this c tau by 24 factor multiplying the z of tau. So you have this, and you're going to now invoke the modular invariance of z naught. Okay. So let's do this. And we're going to then use a saddle point approximation to actually find out what rho is. So, okay, uh, z of tau is equal to this. Now, that's the first line here. Now, remember, z naught of tau is equal to z naught of minus 1 over tau. So that's what this particular replacement is. I've just replaced this guy with this. And now I will use the fact that, if you use this formula again. So if you use this formula again, you can write z naught of minus 1 over tau in terms of z of minus 1 over tau. I've missed a minus. Give me a second. Minus 1 over tau. So now we have two factors, okay? Now you have this factor, which was there from earlier. Now you have a 1 over tau as well. So now what? Now, so if you write down rho of h, so rho of h becomes e to the 2 pi I h tau, there is a c tau piece, and there's a c by tau piece. So what is the key to a saddle point integration? The key to a saddle point integration is a separation of the integrand into a rapidly varying phase and a slowly varying prefactor. Okay. Now we are going to assume that 1 over tau varies slowly near the extremum of the phase. This is something that you can prove, and if I have it my way, you guys will prove it in an upcoming assignment. So if you do that, then what you'll see that, so if you do so I mean, you need to extremize this exponent, and the extremum of the exponent is tau is I square root of c over 24h. So if you put this now into the integral, then what we will obtain is that rho of h is given by exponential of this factor into z I infinity. So if you do this, what are you going to obtain? So what you're going to obtain is, now from here it's simple to just say, I mean take the log of this guy, and this is going to be subleading, so you drop that off. So in the limit of large large h, so there's a limit of large h which is happening out here. So what happens is that the log of this rho h bar is given by 2 pi times root over ch over 6 plus c bar h bar by 6. This is a bar. I'm sorry. I don't know where my bar went, but that's a bar. So this is what the entropy is. Okay, so let me actually try to make this a little better. So let's call this guy as Cardi. Okay. I'm sorry, I didn't notice that I'd not written this down. Just give me another second, please. I'm just moving things around. Okay, so I will call this S Cardi. This is given by the log of the number of states, and that is 2 pi times ch over 6 square root plus c bar h bar over 6 square root of that. So this is the entropy of states in a two-dimensional CFT. As you can see from here, this is entirely, entirely, obtained by just looking at what the central charges of these guys would be and what the weights would be. Okay, so that is all. So that's good. And all right, so that was that. Okay. And now this particular formula is going to be something that we are going to see emerge in a very sort of different setup. But this was to give you an idea that just by demanding modular invariance, we have been able to actually get at what the, formula for the counting of states in a CFT would be. All right, so that is it for modular invariance. If there are any questions, I'm happy to address them.
So that formula is valid only for large H, right?
It is valid for large H. There is some very interesting thing that has, so this is what I should point out is this is Carlip's derivation of Cardi's formula. Yeah, so it was initially thought that this particular thing is actually is going to be true only for large charges, but it turns out that what happens is this particular thing seems to work in very many places where it should not work. Okay, so a very recent recent sort of development has been to look at this and try to figure out if there are other ways to try and see. So you can actually bring this a lot closer. So it's not only, so you see that there is large H. So there is, at the end of the day, it's C into H, right? So what happens is that it's not only, so it can be true for large H, it can also be true for large C. So of late, people have been trying to understand this in sort of ways where you are looking at C as being large, and that sort of links up to our holographic things that we're going to just sort of briefly see at the end, where again, when you're thinking about bulk theories which are actually dual to this, you're thinking in terms of large central charges. So in the way that I have described it to you right now, this particular formula is true for large H, but as I'm saying, there are more recent things which people have done, which actually extend the validity of this particular formula beyond large H as well. Okay. Does that answer what you're saying?
Yeah.
Okay.
So this formula gives the entropy of the primaries only, right?
That's another good thing actually. The answer is no. The answer is no. But again, this is something that I could go into in much more greater details. You could figure out. So you see that the partition function that you have seen, right? In that, it's not only the primaries. You have things from all things basically, right? So you have primaries, you have descendants, and everything will actually be sort of counted in that, right? So it's a trace over all of that, right?
Yeah, I think the trace was defined the way it was. Can you just go back to that?
Sure. So let's
trace
go
was
back
defined.
to. So you may be
Not this one, actually. In
confused
the
about
beginning.
something. Let me yeah. So
Okay.
so let me
In
just
beginning of Cardi.
clarify this. Okay. So here, when you're speaking about this particular trace is over the whole of the Hilbert space. Okay. So now what I did in between, which may have got you a little a little confused, is that I defined these characters as well, right?
Yeah.
And where did I do that? I think here somewhere. Each of these guys were actually you know, if you truncated the thing, if you are looking at just one primary,
Yeah.
and all of the things from that particular primary, then you get this this guy. Okay.
Yeah.
And then what is going to happen is that in order to get the full partition function, you need to sum over all of these, all of these primaries as well. But the character for each of them will actually capture the whole Hilbert space, which is under one primary. Okay. But what you had asked actually gives a very interesting thing. You can actually try to figure out what the how you can just sort of focus on the primaries and just and you can rederive something like this, okay, which is exclusively for the just primary fields. And interestingly enough, in that case, if you call that primary, this is just information. I will not be saying more. That actually goes like 2 pi square root of c minus 1 into h by 6. Okay, that's a weird thing, but that is so. The principal part of the entropy is actually going to come from the in this in this particular formula, the main contribution comes not from all the descendants, but from the primary fields in the game. It's not clearly understood why this is the case, but this is
I mean, like, if you take this large h limit, then like the scaling dimensions of the primaries and secondaries like almost equal, right? In the large h limit at least.
Yeah, but as I was saying, it's not only large h, right? It could also have been large c.
Right.
So it's not clear what exactly this this actually entails. But okay, so this is we are going far beyond where we want to go. But I just since you brought this up, this was a nice thing to just point out. Okay. All right, so Cardi formula is something that we have, and for the rest of the class today, it's going to be mainly words. Okay, very good. So we are nearing the absolute end of the course, so let's give you some more gyan. So what we are going to be doing in these last 2 lectures is going to be focused on something called holography. Okay. All right. So any more questions from this, the earlier part of the class? All right, no. So, okay, quantum gravity, right? Quantum gravity, as I write here, is the holy grail of modern theoretical physics. As you guys know well, the standard model of, particle physics, ever since the discovery of the Higgs boson in 2012, this sort of put the last thing down. It's been spectacularly successful in describing nature at energies today. But we know that the standard model does not contain gravity, and hence it cannot be the ultimate theory. It does contain, quantum electrodynamics. It contains the weak force. It contains the strong force, but it doesn't contain. The fourth and in some sense the most important of the forces. So in order for us to have a complete complete theory, one needs to somehow manage to put together a theory of quantum mechanical gravity. As you again know, the standard model, which is based on these other three fundamental forces, is based on the framework of QFT. So it's natural to sort of try to quantize GR as a field theory. But as again I write here, this fails spectacularly. Gravity is non-renormalizable as a field theory. Okay, so one needs to think out of the box. And as you have again seen a little while earlier, a few days earlier, one of these more successful attempts has been string theory, which we briefly encountered before. And now what we're going to do is we're going to meet another even more intriguing way of trying to do this. All right. So that's where we are at. So again, let me just briefly say what we want to do. So what is the holographic? What is holography, if you may wish, or the holographic principle? The holographic principle is perhaps one of the most striking ideas in modern theoretical physics. And this statement, if you wish, is the following. So if you have a quantum theory of gravity in a certain space-time M, this theory is exactly equivalent to a quantum field theory which is without gravity and lives in one lower dimension on the boundary of the space-time M. Okay, so you think of a ball, if you wish, a hollow ball. So inside, so there are two theories. One which lives in the inside of it. That is the theory of gravity, and one which lives on the surface of it. That is going to be the field theory. I should have drawn some more nice pictures for you here, but maybe next time around. Now, what happens is that this apparently bizarre statement, is actually exemplified in string theory through what is called the alias CFT correspondence that is due to Juan Maldacena in 1997. So what does this say? The alias CFT correspondence says that type 2B superstring theory on ADS5 cross S5 is dual to n equal to 4 supersymmetric Yang-Mills in D equal to 4. A lot of words, a lot of things that do not make sense to you. But the point is there's some sort of string theory on an antidesitter background times some 5 sphere is dual to something here. Okay, this something is n equal to 4 supersymmetric Yang-Mills theory, is actually an interacting quantum field theory which exhibits quantum conformal invariance. Okay, so this means that if you're thinking about the beta functions of that particular theory, the beta functions of that theory are identically equal to 0. So in D equal to 4, so the statement goes that there's some particular theory of gravity here. In this case, it's a string theory that lives in antidesitter space in 5 dimensions times an S5, which is not going to be that important to us. And this is dual to this very, so there are these two very different looking theories, and the proposal is that theory A is exactly equivalent to theory B. So that means for whatever observables you can actually compute in theory A, you are going to get an equivalent thing in theory B, and these answers are going to match. So there's going to be a dictionary between theory A and B, and you would be able to actually sort of match them if you wish. Very good. So ADS CFT is a particular manifestation of the much more general idea of holography. Holography says that any quantum theory of gravity should have an equivalent lower dimensional field theory dual. So yeah, ADS CFT is one example where the bulk theory lives in negatively curved anti-de Sitter spacetimes, and the boundary theory is a CFT. Okay. So these are words that some of you may have had heard before, but let's try and make this a little clearer. So what we will do now is we will try to understand this sort of gauge gravity duality without recourse to very complicated machinery from string theory. Okay, so there are some statements out here. Let me try to clarify. Try to say them, and then obviously we will not be doing a very thorough job of this, but anyway, let's see how far we can go. So I start off with a very, very weird statement that some non-gravitational quantum field theories are in the deep way quantum theories of gravity. What do I mean by a quantum theory of gravity? By this, I will mean that it's a theory which has a dynamic metric whose linearized equations of motion generate a massless spin-2 field that we'll call a graviton. Okay, well, fine. But this particular statement is in direct sort of conflict with what is the Weinberg-Witten theorem. What is the Weinberg-Witten theorem? The Weinberg-Witten theorem says that any quantum field theory which has a Poincare invariant conserved stress tensor does not allow any massless particles carrying momentum which has spin greater than 1. So you can at most have something that is massless with spin 1 and nothing above that. And here I started off with a statement saying that some quantum field theories may be quantum theories of gravity. So what is going on? In order for us to have a theory of gravity, a quantum theory of gravity, we must have a massless spin-2 field. So what exactly is happening? What is happening is the following. Yes.
Can I just interject?
Sure, please.
So can you just explain why graviton has to be spin-2? Where does this come from?
See, the degrees are, so why the graviton has to be spin-2? How do I give you a quick way to understand this? Okay. So if you are looking, so you want something which has, so if you have, okay. So you will, I was actually trying to actually give you guys some particular assignments which will show you some things of this which I should not. So without trying to give that particular bit away, let me try and see what I can do. So all right. So if you think, if you have a spin 1 object, okay, if you have massive spin 1 object, it'll have like, I mean, 3 states, right? I mean, you can write down what. You can write down, for example. So you can start off with you know, I mean, two spin halves. You know how to, I mean, get a spin 1, I mean, and a spin 0 state from that, right?
Yeah.
So similarly, so there is again. So if you are looking at something which is, I mean, spin 2, so I mean, it'll not, I mean, if it has mass, then it is going to have 5 states, right?
Yeah.
So what you want to do, so you are looking at some quantity that is going to be, so you're looking at a field which is a field G mu nu, right?
Yes.
And that particular thing has to also be symmetric.
Yeah.
And so you can try to match what the degrees of degrees of freedom here are, and then you would be able to see that with if you have I mean, the short answer in a sense is that since G mu nu is a 2-indexed object, it will actually correspond to a spin 2 field. Okay. So that's a sort of short answer, and I hope a little bit of the exercise that I'm setting for you guys to do will help you try and understand it a little more. Okay. So, and I'll try and also give you a little bit of more, I mean, more of a reference for this thing. So there's this is called the Weinberg-Witten theorem. So any quantum field theory with a Poincare invariant conserved stress tensor will not allow massless particles with spin greater than 1. Okay, so that is something. So you are in trouble in the sense that in order to have a quantum theory of GR, you must have something which is a massless spin 2 object. But here you have a, I mean, proved theorem by no other than Weinberg and Witten, which says you can't do this. The way around this apparently unsurmountable hurdle is to understand that the graviton actually need not exist in the same spacetime as the field theory itself. Okay. So in order to do that, let's try and understand this a little better. Okay. So so there are more hints of this from black hole physics. So what is the maximum amount of matter that one can pack into a certain volume? This is going to be the amount that is necessary to create a black hole that fills up this entire volume. Okay, so there is nothing more I mean, dense than dense than a black hole. So if a certain volume of space-time is filled up by a black hole, that gives an upper bound on the amount of matter that you can fill up a region of space-time by. If you go to black hole thermodynamics, there is something that was proved by proved by Hawking and Penrose, and this was the fact that the entropy of a black hole is equal to its area. The area of the event horizon of the black hole in Planck units, and there's a factor of 4 here. So this defines, in a sense, the maximal amount of entropy that can be there in a particular quantum gravity theory. But notice a very interesting thing here. The very interesting thing is that the entropy in a theory of quantum gravity is going like the area, right? Remember that usually your, entropy is sort of like the volume, right? In any sort of theory, it's sort of an extensive object in a usual, usual system. If you quantize it in the usual quantum field theory, the entropy scales like the volume of space-time. So now, so if there is a theory of quantum gravity, and if there is a quantum field theory, both of them living in the same number of same particular dimension, then the quantum gravity theory has many degrees of freedom less than a field theory. So this suggests that if a theory of gravity is equivalent to a quantum field theory, it has to live in more number of dimensions. Only then can the entropies match up. Okay. This is sort of the line of argument that was behind the proposal of the holographic principle by 't Hooft and Susskind. Very good. So all of this is there. So now, what can this particular other dimension be? Let's try to figure out if a quantum field theory can associate with it naturally an extra sort of direction. So now let's think of the Wilsonian approach to to RGs. So this gives, as I write out here, an elegant answer to what this extra dimension might be. Remember that a quantum field theory at a particular length or energy scale is related to the same field theory, but at a different scale by the renormalization group equation, right? So this is our, RG equations that you have done. These are beta functions which say how the coupling at a particular energy is going to change. This indeed is a remarkable equation, right? We do not need to know what the behavior of the coupling is at any other length scale in order for us to know what is going on in this scale, okay? So this is a remarkably local equation. You just see that this is something that we need to know only at U, okay, not at some other U prime. And this, in a sense, gives us the hint of what we are looking for. We can think of this extra direction as being the energy scale of the field theory. So that, in a sense, gives us this sort of extra direction. So this is what we want to actually work on. And now, so the idea in a sense is you take a family of field theory. So it's the same field theory, and you can think of it at several sort of energy scales continuously. And in that case, that particular direction of energy gives you your emergent extra dimension, where now your spin 2 field can live. Okay, so let's try to understand this a little better. Now you want to find specific examples of what this could be, and to this end, let's make our equation simple and put this guy equal to 0. If we put this guy equal to 0, in that case we have an extra symmetry, as you guys have learned. So of x mu going to lambda x mu. If you are looking on dimensional rounds, if you're looking at the energy now just scales as u going to lambda inverse of u. Now remember, what do we have to do? We have to find out some particular theory which at constant u is going to give back your quantum field theory on a flat space-time. And you have u now, and there is this extra symmetry which is also associated with these sort of coordinates. So you have d coordinates, mu goes from 0 to d minus 1, and you have this extra direction u, and you have to, what you have to do is you have to construct a d+1 dimensional metric out of this. Okay, if you construct the d+1 dimensional metric out of it, keeping in mind that you have to have a d-dimensional Poincare invariance along with this extra symmetry, what you end up with is the most general metric which can do this is something like this. Okay, we will see this more, but this can be recognized as a metric of ADS d+1, with this L as being the radius of ADS. We'll go into what the geometry of ADS is in the next class, but the upshot of all of this is the following. We see that conformal field theories in d dimensions should be related to a theory of gravity in ADS d+1. Okay, as I have already stressed, the best studied example is the original Mallasena correspondence, which is a duality between n equal to 4 super Yang mills with a gauge group SUN and type 2b superstring theory. But we will focus on the generalities of what the geometry is and see things a little bit. And we will end up by showing you that the field theory analysis of Cardi that we did earlier it actually reproduces what the Bekenstein-Hawking entropy of some particular black holes in ADS give you. Okay, so that's how I want to wrap up the course, but that will be 2 lectures from now. So next lecture is possibly just ADS and some amount of familiarizing yourself with what that is, and then we will try to see I'll say a little bit about ADS3 and then about these black holes and show you how the equivalence works. Maybe I'll say a little bit more. I've not entirely, so that may just be one class, and we will wrap up on Friday. I am still to send out the email, by the way. So Friday it's 10:30. Okay. Okay, so that's what I wanted to end with today, and so that is about it. So I'm happy to answer any questions if you have them. Okay. If there are any questions, please feel free to ask.
Hello, sir.
Yes.
Sir, can you please move to the page where you have mentioned about Weinberg-Witten theorem?
Sure. Yep.
Sir, in this theory, the theory doesn't allow any massless particle, right?
Massless particles of spin,
Yes.
which is more than one.
Yes. So there can be massive particles, the theory allowing.
We want to understand gravity,
yes.
right?
Yes.
And as far as we can understand, gravity there should not be any mass of the graviton. So you could try to say that maybe this has a very small mass or something like that.
Yes.
But that doesn't really help you in the sense that so if you were to quantize things in the same way, you wouldn't really so then the idea of holography is based on something where you are not looking at least the low energy theory is something that reduces to Einstein's GR. Okay.
Okay.
You're not looking at, I mean, exotic theories like, yeah, so things like massive gravitons have a lot of problems if you try to quantize them. I mean, on top of being troublesome in the usual way, there are also, I mean, other sort of problems with it, so that doesn't really help you.
Okay. Okay. Okay.
Also, if you have this mass, then this u going to u by lambda symmetry, like that is not there, right? In
Yeah, so the
RG equation.
whole thing will just drop off, right? Because
Right.
then you don't really need to think of an, I mean, extra direction. So Shoigot, I guess, was saying that maybe you can circumvent by saying that you could just have something which is a small mass object.
Yes,
and
yes,
so
yes.
on.
I was thinking. Okay.
Yeah.
Okay. No.
But then in that case, you don't even need this, I mean, extra direction, right?
Extra direction, yes.
So yeah. So yeah, so that's not the way that we are trying to go about it. Yes.
Okay.
So is it also because the gravity has to be long range?
Yes, that's right. So we know that it is long range, right?
Yeah.
We know that it's extremely long range. So if there is a mass, it has to be a very, very, very teeny tiny mass, basically. Which is, I mean, which also has, I mean, other sort of problems of yeah, I mean, things like negative norm states and so on and so forth. So yeah, so that's a I mean, sort of Pandora's box that you do not want to open. So yeah, no, but people actually do try and look at things like that as well. They have been, there still are actually a large number of I mean, attempts at looking at massive gravitons and so on and so forth. I mean, what I would say is that sometimes they can be an interesting, I mean, sort of toy problem for something. But if you are looking at gravity, I would really think that, I mean, I wouldn't want to replace Einstein's gravity by something at the classical level. So yeah. All right, any more questions? So let me actually stop the recording.